In this session, we're going to talk about variable rate nitrogen management, but first we have to understand what goes into nitrogen requirement. So when we talk about site-specific nitrogen management, we're going to talk about the two different approaches, the predictive approach and the reactive approach. So the predictive approach is zone-based. Often nitrogen recommendations are based on yield. So early on we thought, well, it makes sense to take a yield map, apply our yield-based nitrogen recommendations to that yield map and vary nitrogen in that way. But what's causing this yield variability? Can it be corrected through other precision ag techniques? Because we don't know that that yield variability was caused by nitrogen. So we might be compounding problems if we're changing nitrogen rate based on yield. Its yield zones vary year to year. Yield and nitrogen relationships are complex and inconsistent. So I would argue that a zone-based predictive prescription for nitrogen is probably not the best way to go, because the temporal variability in nitrogen requirement far outweighs the spatial variability in nitrogen requirement in most cases. So we need a site-specific nitrogen management tool that is going to address that temporal variability year to year. And that's a reactive approach. And there's a lot of sensors on the market now that can be used in this strategy. So again, to remind you about precision and accuracy, because this is kind of underpins everything we do in site-specific nutrient management. Yield-based nitrogen recommendations are highly accurate, okay, because they're developed over many years from many plots, and on average they're right. But every single year they're wrong. You know, it's just like the low precision, high accuracy target. On average we have the right rate, but each year we're not hitting the bullseye. So what effect does this lack of precision have on our nitrogen use efficiency? Again, it's a diminishing return function, as this figure shows. We look and we see that as yield goes up with nitrogen rate, we reach an optimum. Now, on the left-hand side of that optimum point, the economic impact of under-fertilization is greater than the economic impact of over-fertilization. But what happens when we look at different years? Changes across time really mess us up. Now here I'm going to take some real data, but then I'm going to model it in a hypothetical way to look at soil nitrate in the top meter in different years with different yields. So in the first year we're getting about 150 bushels per acre at our optimum. And then we can have a year in year two with much higher yields, up around 250 bushels per acre. And then in the last year, we had really poor yields. That was a drought year where I was doing this research. So here are our three optimum nitrogen rates for each of those years. And now we're going to look at the nitrate in the top meter under those. And we see that the nitrate in the top meter starts to go up exponentially right at that optimum nitrogen rate. In the good year, we have very little nitrogen leaching. One of the best things for nitrogen use efficiency is plenty of rainfall, because moisture has the most to do with nitrogen use efficiency in many situations. But in that last year, where we didn't get good yields, we lose almost all the nitrogen we apply, even if we're applying at the right rate. So it gets really tricky managing nitrogen across time with different amounts of rainfall. So here's that data in a tabular format, and we see that the 1 meter nitrate concentrations in site year 1 is about 50 pounds per acre, and in site year 2, it's about 28 pounds per acre. And then finally, we have almost 100 pounds per acre that are lost in site year 3. And so if we apply nitrogen at different rates, 185 pounds per acre or 250 pounds per acre, each year for each of those three different scenarios, we end up with very different nitrogen loss amounts. So if we applied 150 pounds of nitrogen per acre, we'd be doing all right in site year 1 and 2, but in site year 3, we're really blowing it up. And then if we said, well, I'm going to fertilize for that high yielding year, I'm going to put 250 pounds of nitrogen per acre down. Again, we're doing all right in site year 1 and site year 2. We're losing a little bit more nitrogen, but we're losing a lot of nitrogen in that third year. We're even losing nitrogen that mineralized out of the soil, and we're losing a lot of money. So we have to address this temporal variability. We just can't apply the same amount of nitrogen every year. So in this example, I've got 3 different field sites where we put out different nitrogen rates and measured the yield. And 2 of the sites respond as we expect to nitrogen. 0 in, we get low yields, and we add some nitrogen and we start to optimize our yields. But we've got this one site that sticks out. We got 160 bushels per acre with 0 pounds per acre of nitrogen applied. What happened here? Well, this was a corn crop following alfalfa. Here's another example, very similar, same year, 2008. In this example, there was 3 years since the last organic nitrogen application. It was a manure application. It was at this site we call Clarksville, and we got almost 200 bushels per acre with 0 pounds per acre of nitrogen. And in the last example, this is the most stunning. We got over 200 bushels per acre of corn, and it had been 18 years since the last manure application or organic nitrogen source was applied, and that was a historic swine manure application. And so how many of us think we can get 205 bushels per acre with no nitrogen applied? Well, the trick is we don't know when that's going to happen. In these 3 examples, what happened in 2008, this research was done in Maryland. Around Memorial Day weekend, we had over 100-degree temperatures for 3 days in a row, a very moist spring, and so we got a lot of nitrogen mineralization out of the organic matter in these soils. So basically what we had been put in the savings account in organic matter, we got paid back in 2008 because of the weather pattern. It wasn't just the warm temperatures, and it wasn't just the rainfall. It was when they occurred and how they occurred. So, in those previous examples, we got 160 to 200 pounds per acre of plant available nitrogen, and it was a combination of weather and previous management. There's no way to predict this before the season, but we have some ability to predict it in season through fertilization in season. And that's why in nitrogen management in corn, even outside of precision ag techniques, split applying nitrogen, putting it on in season is one of the strongest tools we have. Because regardless of everything else, soil texture, cropping system, 30 to 40 days inside that season, we have more knowledge. And if you have more knowledge, you're smarter, and you can make better decisions about your nitrogen management. So let's talk about nitrogen requirement. It's very complex in cereal grain crops. Its nitrogen requirement to achieve maximum yield is determined basically, it's a function of 3 different things: nitrogen responsiveness, nitrogen availability, and potential yield. All 3 factors vary spatially and temporally. That means in space and time. And all 3 factors are independent of each other, all right? And so that really makes it very complex. Soil type, climate, previous management, these things can all influence the yield potential, the nitrogen availability, which is the nitrogen we're getting from the soil, and nitrogen responsiveness. Nitrogen responsiveness is tricky as well. That's how many bushels we get per pound of nitrogen that we apply. So surpluses, when we overapply nitrogen, are due to our recommendations and the fact that they can't really account for seasonal and spatial variability. When we talk about managing nitrogen in season and doing variable rate nitrogen management, the reactive approach using sensors is going to work out. It can address that temporal variability because if you go in and sense that crop at V6 to V10 in a corn crop, you're kind of integrating the climate and weather patterns that you've had over that past 30 to 40 days since you planted the corn. The one thing about sensors is there's mainly 3 different sensors on the market right now, but it's not the sensor as much as the algorithm and the recommendation system behind it. You need a system that addresses this nitrogen requirement, which is made up of nitrogen responsiveness, nitrogen availability, and potential yield. And it should address them independently across space and time.